Assalamu alaikum. In the previous lectures, we have talked about design of lead compensators and design of lag compensator. Lead compensator is utilized to improve the transient characteristics, and lag compensator is utilized to improve the steady state errors. If for a particular system both the transient response specifications and steady state error requirements are not fulfilled, then what we have to do is we have to cascade both the lag compensator and lead compensator to the system so that design specifications are achieved. And in today's lecture, we shall talk about design of lag lead compensator, which is utilized to improve both the transient characteristics and steady state characteristics. To understand it, we explain it with the help of one example. The system that we have is given by, we have this system, unity feedback system, and for this particular system, without use of any compensator, we can determine its transient and steady state characteristics. To determine the transient characteristics, we find the closed loop transfer function, which is given by g of s over 1 plus g of s. For this uncompensated system, the location of closed loop poles is, there are two complex poles which are located at minus 1.79, and it is a third order system, so third pole is located at minus 12.41. This third pole we can see is less dominant, so this particular system gives us an overshoot of 20%. It can be computed by computing zeta and omega n, and then overshoot can be computed. And this also gives the settling time of 2.23 seconds. We are satisfied with the overshoot. However, what we want to achieve is we want to reduce the settling time. So our first design requirement for this particular system is reduce settling time by 2 times. What about steady state errors for this system? We can see that it is type 1 system. So steady state error for step input will be definitely 0. Steady state error for ramp input can be computed. Steady state error for ramp input is given by 1 over kv, where kv is equal to, you know that limit s tends to 0, s into g of s, which in this particular case comes out to be 192 divided by 60, which is equal to 3.2. And corresponding steady state error comes out to be 1 over 3.2. We want to improve steady state error by 10 times. So this is our second requirement. So these are our design requirements. We want to improve the transient characteristics. We want to improve the steady state characteristics. By improvement in error, we mean reduction in the steady state error. So the design procedure is just the same as we have already discussed. To achieve the transient requirements, we cascade lead compensator, and to improve the steady state characteristics, we cascade lag compensator over here. So we discuss both of them, design for both of these compensators over here. So what we desire is this 2-fold reduction in settling time means that we desired overshoot. We are satisfied with 20% overshoot. However, settling time, which you know is 4 over zeta omega n, we want it to become 2.23 over 2. This is desired settling, desired requirements. If we do not want to change overshoot, then zeta must remain the same. Zeta for this system which can be computed from these poles, that is 0.456. And we do not want to change zeta, so to reduce the settling time, what we can change is omega n only. Therefore, desired location of closed loop poles, this was actual location, this term is zeta omega n. So if omega n has increased by 2 times, so desired location of closed loop poles, dominant closed loop poles, will be this multiplied by 2 and this multiplied by 2, because new value of omega n is twice the existing value of omega n. So this comes out to be equal to, if we sketch the root locus for the actual system, it is given by this graph. We have one pole at origin, another pole at s equal to -6, so 1, 2, pole at s equal to -10, another pole at s equal to -6. Root locus can be sketched for this system. We can see that this is part of root locus, this is part of root locus. Root locus starting from poles, finite poles, will terminate at zeros, which in this case lie at infinity. So this is root locus starting from this pole is already approaching infinity. Root locus which emerged from these two poles will follow asymptotic lines to reach to zeros at infinity. Angle of those asymptotic lines and center of asymptotic lines can also be determined. So here is a sketch of the root locus for this system. Our desired closed loop poles are at this point -3.59. So here is 6, so 3, 3.59, and J7 is somewhere over here. This is the desired location of closed loop pole, and of course complex conjugate must also exist. We can see that root locus is not passing through desired closed loop poles. So what we shall do is we shall design a lead compensator. Lead compensator will contribute some additional angle, and the angle condition will be satisfied for these points, and hence root locus will new root locus will pass through these desired closed loop poles. You know the design procedure for the lead compensator. The transfer function of lead compensator G lead is given by Kc S plus Zc over S plus Pc. So the value of Zc and Pc is selected such that angle condition is satisfied for these points. So the choice for Zc and Pc, there are infinitely many different choices which will fulfill the requirement. So what we do is we arbitrarily place one of these, either 0 or the pole, and then determine the location of the other thing. For example, we place 0 of the compensator. Let's place it over here, just overlapping with the pole of the system. 0 of the compensator is placed over here, and then the location of the pole of the compensator, this is Zc, this can be determined minus Zc, sorry, not Zc, minus Pc. Therefore, we have selected Zc as plus 6, and we are required to determine the location of the pole. So the location of the pole will be selected such that angle condition is satisfied. Here at this point there is an angle contribution due to this pole, and let's call it theta 1. There is an angle contribution due to this pole, let's call it theta 2, and there is an angle condition due to third pole, and the angle contribution due to this 0 of the compensator, and angle contribution due to pole of the compensator. So theta 0 angle contribution due to 0 of the compensator minus theta p angle contribution due to pole of the compensator minus theta 1 this angle contribution minus theta 2 minus theta 3 that must be an odd multiple of 180 degrees for the angle condition to be satisfied for this point. We have selected this 0 just overlapping with this pole, so this angle contribution due to 0 is the same as angle contribution due to this pole theta 2, and rest of them can be computed. Theta p minus what is theta 1? Theta 1, this angle is 180 degrees minus this angle. What is this angle? This angle is tan inverse of this length divided by this length. So tan inverse of this length is 7 and this length is 3.59. Angle contribution theta 1. And then what is angle contribution theta 3? That is tangent inverse of this height, which is 7, divided by this thing. What is this length? This is this total is 10 and this is 3.59, so 10 minus 3.59, and we want it to be equal to minus 180 degrees. After all these computations, theta p, the angle contribution, theta p, the angle contribution due to pole of the compensator, that comes out to be equal to 15.3 degrees. So this pole will be placed at a location such that the angle contribution due to this pole will be 15.3 degrees. So now we know this angle, therefore location of this pole can be determined. So let's determine it over here. So we can see that this tan of this angle, tan of 15.3 degrees, is equal to this height, which is 7, divided by this length. This length, let's call it x. So this is x, and from here x comes out to be equal to 25.58. Then what is the location of the pole? So this length we have computed, 25.58, plus this length, which is 3.59. So PC is 25.58 plus 3.59, which is 29.12. Therefore, to achieve these transient characteristics, the pole and 0, this is one choice. Of course, this is not the only choice. So hence we have this designed compensator. Now, how to determine this Kc? For this point to be a closed loop pole, the angle, the magnitude condition must also be satisfied for this point. That is g of s into g lead, this lead compensator of s at s equal to this desired point minus 3.59 plus j7, that must be equal to 1. So just by substituting the numerical values, g of s is given by 192 over s, s plus 6, s plus 10, and the lead compensator Kc, s plus 6 over s plus 29.12, its absolute value at s equal to this point, let's call it s1, this point, this is equal to this s plus 6 cancelled out with this s plus 6, so 192 divided by, substitute this s1 over here, minus 3.59 plus j7, and s plus 10 minus 3.59 plus j7 plus 10, and then this thing multiplied by kc over minus 3.59 plus j7 plus 29.1. So absolute value of this expression must be equal to 1. So this is equal to 192 over absolute value of this is square of this plus square of this whole square root. So that is equal to 61.9, and then absolute value of this is equal to absolute value of the real part, which is 10 minus 3.59, and square of this real part plus square of the imaginary part whole square root, that is equal to 90.1, and then kc over this absolute value of this complex number, which comes out to be equal to 700.8, square root of 700.8. So this must be equal to 1. From here, value of kc can be computed, which comes out to be equal to, kc is equal to 10.29. Hence, the transfer function of the lead compensator here comes, kc comes out to be equal to 10.29. So we have achieved the required transient characteristics, and to improve the steady state characteristics, we shall now design a lag compensator. The requirement was 10 times increase, 10 time improvement in the steady state characteristics. For the original system, uncompensated system, kV, we have found it that was equal to 3.2. Now we have augmented lead compensator to the system, that is here we have g of s, we have augmented lead compensator to the system, and this has not only improved the transient characteristics, but it has also effect on the steady state requirements. So let's see what is the steady state error for this system. That is, the transient characteristics have been improved. We are still left with the steady state characteristics. So let's determine kV for this system. kV for this system, that is limit s tends to 0, s g of s into g lead of s, that we have designed over here, that comes out to be equal to this s, we just substitute it over here, s tends to 0, 192, here is also s plus 6, s plus 10, 10.29, s plus 6 over s plus 29.12. So after substitution of this limit, kV is equal to 6.79. What is desired? Desired kV? We want steady state error to reduce by 10 times, that is kV, desired kV is, we want it to be equal to 32. We have, this is desired. Now this is kV for the system augmented with lead compensator. So how much improvement do we require? The improvement that is still needed is 32 by 6.79. That is improvement, which comes out to be nearly equal to 4.71. So design of lag compensator is very easy. You remember GC of S, let's call it lag compensator. That is given by S KC S plus ZC over S plus PC. This KC is always comes out to be nearly equal to 1. This ratio ZC and PC is selected to be equal to this one. So let's place the pole at S 0.01. Then the location of 0 is this much times 0.01, which is 0.047. So our lag compensator, we have also designed the lag compensator, and that will achieve the required steady state characteristics. So designed lag compensator. So we shall cascade this lag compensator to the system as well, so that both the transient as well as steady state error requirements are satisfied. The overall transfer function of the compensator is just the product of these two compensators. So GC of S. So this is our lead lag compensator. Now, how to practically implement this compensator on your system? So this compensator can be implemented using electronic components. Let's see how this controller will be practically implemented on your system to achieve the desired characteristics. So as a homework, you have to simulate the system in MATLAB, this actual system, and the system with the lag lead compensator to verify whether our design requirements, that is the transient and steady state requirements, are achieved or not. So you have to do it by yourself.